Magnemotion's maglev provides a low-cost, high-speed, highly efficient, and safe solution which addresses today's urban transit needs. Magnemotion's urban maglev transit system is based on an electromagnetic suspension, or EMS. This suspension system uses the attractive force between permanent magnets on board the vehicle to steel on the guideway to suspend and guide the vehicle along the track. As demonstrated in our test system, Magnemotion's maglev is the optimal design for urban maglev systems because it uses less power and provides levitation at zero speed. This is an advantage when considering the frequent starts and stops that are usual in an urban setting. In addition, an elevated guideway and wraparound vehicle design ensures that a vehicle cannot be derailed under normal operating conditions. The permanent magnets on board the vehicle generate field strength to obtain the suspension force needed. The use of permanent magnets allows operation at a gap of 20 millimeters, a very wide gap for an EMS suspension system. This also reduces the power required for levitation to less than 200 watts per ton. Coils placed around the magnets on the vehicle allow the suspension system to be stabilized. The suspension, guidance, and thrust forces on the vehicle are all produced by the same magnetic structure, which reduces the weight of equipment on board the vehicle and guideway, lowering the overall system cost. All of the levitation control hardware is contained on board the vehicle. We can see the 3,000-pound demonstration vehicle lifting off first from the parked down position where the vehicle is at rest against the guideway surface. Power is applied to the levitation coils, which increases the magnetic attractive force of the vehicle to the guideway, lifting the vehicle to its nominal operating gap. We next see the vehicle lifting off from the parked up position where the initial gap is small and the magnets are touching the steel surface of the guideway. In this case, the levitation coils are driven to reduce the magnetic attractive force of the vehicle to the guideway, allowing gravity to pull the vehicle away from the guideway. The control system immediately adjusts the vehicle to its nominal operating gap. When levitated with no propulsion, the vehicle floats in a friction-free state. Offset magnets provide lateral damping to stabilize the vehicle during high wind conditions. Next, we see the propulsion system moving the vehicle along the guideway. The vehicle accelerates at a rate of 2 meters per second squared to a peak speed of 2 meters per second, which is limited by the length of the indoor guideway. The maximum speed for a full-scale system is 60 meters per second. The vehicle decelerates to stop at the intended indexing point, again at a rate of 2 meters per second squared. The vehicle indexes to the intended station location with an accuracy of better than 10 millimeters. All of the propulsion control hardware is located on the guideway. No power is transferred to the vehicle for propulsion. The magnetic gap of the vehicle changes with the load on board the vehicle. In particular, if you load the vehicle more heavily, it operates with a smaller gap. And if you have the vehicle empty, it operates with a larger gap. Over the load range and vehicle weight, we see an operational gap variation of plus or minus 3 millimeters. The system design ensures that the force from the permanent magnet exactly matches the force from gravity on the vehicle. Taking advantage of the permanent magnet field strength, Magnemotion's maglev system provides a levitation system that consumes less than 200 watts per ton. This is approximately 5 times lower than competing maglev systems. Magnemotion's maglev system consists of multiple vehicles traveling with short headways, which require a simple but sophisticated control system. Maglev and linear synchronous motor technology coupled with Magnemotion's sophisticated control provides the next generation transportation system. Magnemotion, a force in electromagnetic systems.